Bismillahirrahmanirrahim. In the name of God, the most gracious, the most merciful. Today's proof by contradiction is a proof on prime numbers. And just to start off with, have a look at these three and try to think, why are they prime numbers? Okay, hopefully you're happy 17 is a prime number. Why? Normally we say that it can't be divided by anything except itself or 1. Same with 19, same with 23. But let's look at that in a bit more depth, because we need a simple way of writing that. So the other way we can say about this is that if I divide 17 by 2 or any other number, then I'm going to get a remainder. And the easy way to write that is to say, look, I can take 2, times it by 8 to get me close to 17, but then to get to 17 I'll have to add 1. So that means that I'm going to have to, so that means it's not a prime number, it is a prime number because I can't divide it by 2 perfectly. If I divide it by 2 I end up with a remainder, so it's not a perfect division, and that means 2 is not a factor of 17, so that means that if it doesn't have any factors then it's a prime number. Another way I could do it is, but then I can't just stick with 2, I have to go with all of them. So I can repeat the same kind of thing with 3. Does 3 go into 17? No, it doesn't. It'll have a remainder. How can I show it's gonna have a remainder? I can do 3. I can rewrite 17 as 3 times 5, and then add the 2 to make it up to 17. 3 times 5 is the closest I can get to 17, but then I have to add a 2. So here, because I've got a remainder, it means that it couldn't be divided by 3 perfectly, so it's a candidate for a prime number. As long as I can show that for every other number, then it will be a prime number. So let's just go with 5. 5 would have to be times by 3 to get close, and that would make 17. Again, I've got a remainder. Only when I don't get a remainder, then I know it can be divided, so that would mean it's not a prime number. But as long as I keep getting remainders, then it's going to be a prime number. So let's try 7. 7 would be times by 2. I'd have to add a 3. That's the remainder. Again, I've got a remainder, and this is now looking like it's going to be a prime number. So you can repeat that with 11, 13, every other prime number, and then you'll run out of numbers to divide into. Every number gets you a remainder. So if you ever do get a number where it's dividing perfectly, so let's say 24, if you could show that as 2 times 12, no remainder, that means it's divided perfectly, it can be divided by another number, and that means it's not a prime number. Prime numbers have to have this remainder. So let's look at today's proof, which is, can we prove that prime numbers go on and on and on? So the question is, prove by contradiction that there is an infinite number of prime numbers. I'm just going to put a set of prime numbers. So if you remember the technique from yesterday, last lesson, the day before yesterday, we start by assuming the opposite, because if we can just prove, or if we can just show the opposite isn't true, then the only other option is that the other option has to be true. So if we assume that there is a limit, there is a prime number that is the largest. So if we assume there is a limited number of prime numbers, and then we can do some work on that and then show that if there's some kind of error, then what's the opposite of limited? It's unlimited, so that would be the proof we want. So what's another way of writing this in a bit of a simpler way? Assume there is a prime number that is the largest prime number possible. Okay, let's call that largest prime number possible P, big P, with, let's just say, little n. So the first prime number P1, second prime number P2, third prime number P3, and let's say the list goes on and on and on until we get to a number that's the biggest prime number. There's no prime numbers after that. I'm going to call that Pn. So we've got P1, P2, P3, all the way up to Pn. And what we're going to do is we're going to times all of these together. Remember that Pn only exists, that's the largest prime number, that only exists if what we're saying is true, that there is a prime number that is the largest prime number possible. So we have to just go with it. Assume that it exists. Let's then times all the prime numbers up to that one together, and let's add, just for good measure, let's make that one bigger by adding 1. So here I'm adding 2, the first prime number, times 3, the second prime number, times 5, the third prime number. Keep on doing that until you times by also the biggest prime number you think exists, and then whatever the answer is to all of that multiplication, let's add 1 to that, and let's call our answer, let's give our answer a name, let's call it n. So what do we know about n? Apart from it's a very, very big number, it's made up of lots of prime numbers, plus 1. What do we know? What we know is that if I try dividing this big number n by the first prime number, then I'm going to get a remainder of 1. Just like earlier on when we were looking at 17, and we wrote 17 can be written as 2 times 8 plus 1, that remainder 1 helped show that it couldn't be divided by 2, but if you do divide it by 2 you'll get a remainder of 1, so it can't be divided by 2 perfectly. So here we know that this big number n, if we try dividing it by the first prime number, we're going to get a remainder of 1. We can then try it again. We can say, what if we divide it by the second prime number? Again, we'll get it'll divide, but it'll have a remainder of 1. What about the third prime number? We can divide it by the third prime number. Will it divide perfectly? No. It'll have a remainder of 1. And we can apply that to all the prime numbers up until Pn. It'll always have a remainder of 1. And then even by dividing it by Pn, this so-called largest prime number possible, we would still have a remainder of 1. So what we say is that n will always have a remainder when we try dividing by any of the prime numbers up to Pn. So that's a definition, that's a characteristic we've seen before. What do we call a number that when we try dividing it by any number we always get a remainder? What did we call 17? What did we call 19? What did we call 23? The special characteristic those three numbers had is that whenever we tried dividing by anything smaller than 17, that was a prime number as well, we always got a remainder. And here we're getting the same thing. So that means, because we're always getting this remainder of plus 1, we're always getting a remainder, then that means n must be a prime number. And if it's a prime number, we can also see that it must be larger than any of these numbers on their own, because to make n we had to multiply all of these numbers, and also we added 1. So n is larger than all of these numbers, so that's n is larger than Pn, which, hold on, Pn is supposed to be the largest number possible, and we've just shown that we can end up with a new number n which is even larger than Pn. So that means what we had at the beginning can't be true. It can't be the largest, n can't be the largest prime number. Pn can't be the largest prime number. So that means our assumption was wrong, that there is not a prime number that is the largest prime number, which means that we've proved what we wanted to prove, that the prime numbers just go on and on and on for infinity. So a bit of confusion on prime numbers if you don't really know them properly, what prime number is. Very easy to get confused, but if you are comfortable with a prime number, you know that it can be rewritten as a multiplication plus a remainder, then this proof isn't too hard to follow, but it sometimes takes a couple of attempts. So we'll just make a second attempt just to make sure that one of you got it. So we're trying to prove that there is an infinite set of prime numbers. What are we starting off with? What sentence will I start off with? What assumption will I make if I'm trying to prove something by contradiction here about prime numbers? Write down what you think. Okay, maybe a little bit stuck in the first step. You always let the question guide you, and you think of what's the opposite. So the opposite is that there's a finite set of prime numbers, or that prime numbers end sooner or later, or that there's a prime number that's the largest. So any of those three will do, but the easiest one is to go with the prime. We're assuming the opposite. We're assuming there is actually a prime number that is the largest prime number possible. Where do we then go from there? Do you remember what we did then? Good. Then we give it a name. We'll say, let's call that largest prime number possible Pn, and let's give the prime numbers up to that Pn names as well. Let's call them P1, P2, P3. Okay, so we've given them the names, we've listed out the prime numbers all the way up to Pn. Well, what do we do then? We have the sequence, but what do we do with this sequence now? Okay, we multiply it. We say, look, if we've got these prime numbers, what's the harm in multiplying them all together? Let's multiply them all together, and just for good measure, let's add 1 as well. So we end up with a really big number we're going to call n. And now let's try to examine what's special about n. What can it be divided by, or what can't it be divided by? What do we think of first? Dividing it by what? We'll just go in order. We say, okay, what if we divided it by P1, the first prime number? we'd get a remainder of +1. What about if we divide it by the second prime number? Still, that +1 at the end means we're going to get a remainder of 1 by dividing by any of these prime numbers. So we can then say that we'll always have a remainder if we try dividing n by any of they're called prime factors, or any of the prime numbers up to and including Pn. And then we think about that and say, hold on, what does that mean about n? If n can't be divided perfectly by any of these numbers, if it's always going to have a remainder, what does that mean? Good, it means that n itself is a prime number. And if we then think about how we got n, what do we then notice about n? Not only is it a prime number, but it's pretty large as well. In fact, it's so large, it's larger than any of the prime numbers that made it. It's larger than what we thought was the biggest prime number, Pn. So we can say n is larger than Pn, and that contradicts what we said at the beginning, because we said that the largest prime number possible was Pn, and now we've just shown that there's even a larger prime number bigger than Pn. Something's gone wrong somewhere. It must be the starting assumption was wrong, so we can say no, there is no largest prime number. The prime numbers therefore go on and on. That's the proof done. Okay, if that was a little bit hard for you, please feel free to go through the video. Sometimes it takes a couple of rewinds and replays, but that's the section on proof by contradiction finished. You'll be happy to hear. Feel free to go through, you should go through some of the practice questions in the exercise 1A. The book we're doing is the Pearson edXL Year 2 Pure Maths book. Next time we'll look at algebraic fractions, inshallah, if God wills. See you in the next lesson. Assalamu alaikum wa rahmatullahi wa barakatuh.